Does NEI 1804 underuse HAZOP in non-LWR industry and reactors risk assessment? NEI 1804 explicitly includes HAZOP in the development of the PRA for non-LWRs. But look carefully at figure 3-3. My question is, are we using HAZOP too narrowly, and could we use much more of what HAZOP already does from the very beginning of plant design? I want to walk through figure 3-3 exactly as NEI 1804 presents it, and then rewind it and show you an alternative pathway, not to replace PRA, not to replace the LMP methodology, but potentially to create a more systematic and traceable pathway from plant design to hazards and risks, and then to design improvement, and then to PRA, and finally to LBEs. NEI 1804 explicitly includes HAZOP in the development of the PRA of non-LWR industry and reactors. Let's start here. Plant design concept. NEI 1804 recognizes that LBE development begins very early, when many design details may not yet be available and the PRA may not yet be mature. At this stage, an initial set of LBEs is proposed using engineering judgment, relevant experiences, and available design information. NEI 1804 also recognizes that this initial set may not be complete. As the design matures, the PRA matures with it, and the LBEs are progressively refined. So let's follow figure 3-3. From plant design concept, we move to plant functional analysis. NEI 1804 identifies three fundamental safety functions: control heat generation, control heat removal, and retain radionuclides. These establish the fundamental safety objectives that the design needs to achieve. We need to understand where radioactive material exists and what needs to be done to prevent the release of those materials. That leads directly to the next step. Now we are identifying the barriers that are responsible to retain those radionuclides. This is important because the PRA ultimately needs to understand the event sequence that could result in a release of radioactive material. NEI 1804, therefore, builds much of this structure and architecture around protecting those barriers. The next question becomes, what functions are responsible to protect each barrier? NEI 1804 calls these PRA safety functions, or PSFs. A PSF is essentially a function modeled in the PRA that prevents or mitigates a release of radioactive material. So now we have moved from what needs protecting to what safety functions provide that protection. The next question is, what SSEs and operator actions actually perform those PSFs? SSC means a structure, system, and component. A structure could be a physical barrier or supporting structure. A system could perform a safety function such as heat removal. A component could be an individual pump, valve, sensor, actuator, or other item within that system. And operator actions can also contribute to the required safety function. So figure 3-3 has now established, starting from radionuclide source to barrier, and then to PSF, and then to SSC and operator action. And now we have reached the part that particularly interests me. The next box asks us to identify the failure mode of each barrier and SSC performing PRA safety functions. And figure 3-3 explicitly shows HAZOP and FMEA as system engineering inputs into the PRA development process. This isn't accidental. NEI 1804 says that before the first design specific PRA is introduced, we need a technically sound understanding of potential failure modes, how the plant responds to those failure modes, and how protective strategies can be incorporated into the safety design. It specifically identifies early safety analysis methods such as FMEA and PHA as ways of making those evaluations systematic, reproducible, and as complete as the current design stage permits. And elsewhere, NEI 1804 explicitly identifies HAZOP as one technique that can support the initial selection of LBEs. So HAZOP clearly has a legitimate role here. Once those failure modes are understood, figure 3-3 moves to identify challenges to preventing barrier and SSC failure mode. In other words, what could challenge these functions? What circumstances could cause these barriers, systems, or components to fail? And what combination of failure or conditions need to be considered? This information then contributes to something extremely important. Now we are where the exhaustive enumeration of reactor-specific initiating events start. This is where the relationship becomes particularly interesting. NEI 1804 says that HAZOP and FMEA can be applied during design development to identify initial failure scenarios and support the initial PRA tasks to define initiating events. So we are moving from failure modes to challenges and from there to initiating events. Then, how does the plant respond to those events? The initiating event occurs. Different SSCs and functions may succeed or fail. Operator action may succeed or fail. Barriers may remain effective or become challenged. And these combinations develop into event sequences. Those event sequences become fundamental building blocks of the PRA. NEI 1804 says the PRA systematically enumerates event sequences and evaluates their frequencies and consequences, including uncertainties and common cause failure. I'm going to stop the conventional pathway here because I'm not proposing to replace PRA. My question is about what happens before we get there. Now let's rewind figure 3-3 all the way back to plant design concept and ask a different question. What if we use the full systematic capability of HAZOP from here, meaning from plant design concept? In process industries, we don't necessarily wait until individual safety-related equipment has been identified before systematically challenging what can go wrong. We can start with the design itself. Take the plant, break it into logical HAZOP nodes. establish the design intent of each node, then systematically challenge the intent using guide words and process parameters such as no flow, more flow, low pressure, high temperature, etc. Each credible deviation then becomes the beginning of a structured engineering investigation. Then, by using a brainstorming methodology, we figure out what are the potential causes for those deviations and initiating mechanisms. And then we look into the immediate physical effects step by step. We take them up the escalation ladder one by one, define the consequences. And at the end of that, we get a final ultimate consequence for each escalation pathway. And finally, the ultimate credible consequence is defined. Now we have created a traceable scenario from the physical design itself. But we don't stop at the consequence. We identify the existing preventative safeguards, mitigative safeguards, barriers, safety functions, SSCs, and operator actions. Then we challenge them. Is the safeguard actually effective against this particular scenario? Is it independent of the initiating cause? Are two apparently different protection dependent on the same system? Could they be defeated by the same common cause? Are we relying excessively on one layer of protection? And what happens if that layer fails? Now we have something very interesting. We have systematically connected plant design to the deviations. And from there, we find out what are the initiating mechanisms, and then what is the escalation path and ultimate consequence, and how they are connected to the protection architecture. And from here, I see two complementary pathways. The first is the established NEI 1804 pathway. The HAZOP information can support the identification of failure scenarios, initiating events, and event sequences. The PRA then performs the rigorous probabilistic modeling. It evaluates system success and failure. Those event sequences can then be grouped into event sequence families, which support the identification and refinement of the LBEs. NEI 1804 explicitly explains that PRA event sequences are grouped into families based on similar initiating events, challenges to PSFs, plant responses, and end state. Eventually, we arrive at the LMP decisions around LBEs, SSCs, and DID. Nothing I'm proposing removes that pathway. The second pathway is my proposal, a supplementary LOPA pathway. LOPA stands for Layer of Protection Analysis. This second pathway is my proposal. It's not a requirement of NEI 1804. For selected scenarios identified by HAZOP, we could perform a LOPA. Instead of immediately building the complete probabilistic model, LOPA asks a narrower engineering question, which is, for this particular scenario, do the existing independent protection layers provide sufficient risk reduction? We begin with the initiating event frequency, then identify which safeguards legitimately qualify for credit as independent protection layers or IPLs. We challenge their independence. we challenge their effectiveness. We consider the probability of failure of those layers, and we estimate the residual scenario frequency. This gives us something extremely useful for design decision making. How much risk reduction do we currently have, and how much additional risk reduction might we need? If the existing protection architecture is inadequate against an appropriately established risk criterion, we have identified a risk reduction gap. And that leads directly to engineering recommendations. Perhaps the initiating cause can be eliminated. Perhaps the design can be inherently safer. Perhaps the SSCs needs greater reliability. Perhaps another genuinely independent protection layer is required, or an existing dependency needs to be removed. Or perhaps the architecture is already adequate. The important point is that the result can be fed back into the plant design. That is the important part of this pathway. So let's return to figure 3-3. NEI 1804 already recognizes HAZOP. It already recognizes its contribution to identifying failure scenarios and supporting initiating event development. And it says something even more significant. Traditional system analysis technique, including FMEA and HAZOP, which were used to define LBEs for currently licensed reactors, have been incorporated into the PRA methodology for selecting initiating events and developing event sequence models. So my question isn't, should HAZOP replace PRA? Absolutely not. My question is, are we using enough of HAZOP capability? Instead of using HAZOP primarily as one systems engineering input supporting failure modes and initiating event identification, could we exploit its full systematic scenario development capability from plant design concept onwards? Could we create a continuous traceable chain from plant design to design intent, deviation, cause, escalation, ultimate consequence, safeguard, initiating event, event sequence, and then PRA, event sequence family, LBE, LMP decision? That is what I'm asking. And could a supplementary LOPA pathway provide earlier transparent insight into protection layer adequacy and potential risk reduction requirements, feeding improvement back into the design before the PRA reaches full maturity? I don't believe that question should be answered theoretically. It should be tested instead. Take one representative system, apply the conventional figure 3-3 approach, then apply the expanded HAZOP approach to the same system. Compare the initiating events, compare the event sequences, compare the dependencies and safeguards identified, compare the design insights, and then ask one question. Did the expanded HAZOP approach identify anything? If the answer is no, we have learned something useful. But if the answer is yes, then perhaps HAZOP has got more to contribute to non-LWR risk assessment than figure 3-3 initially appears to suggest. Thank you.